In this video, we're going to talk about derivatives of polynomials. So we're going to see a few different rules for how to take derivatives quickly. All of these rules come from the limit definition of the derivative. But in practice, when we want to calculate a derivative quickly, we don't actually use the limit definition. We actually use the rules. So let's jump into our first rule. Here it is. And in this context, C is going to represent any real number. So it's just a constant. And this expression d by dx out here, that represents the derivative. So what this says is that the derivative of a constant is equal to 0. Okay, so let's jump into an example. We've got an example right towards the bottom of the page here. So in the left column, we've got a few different functions, and in the right column, we're calculating f prime of x, or in other words, the derivative using our rule. Well, anytime our function is constant, the derivative is going to be 0. So if our function is 7, derivative is 0. If our function is minus 4 root 3, our derivative is 0. If our function were, say, pi cubed, again, that's a constant, so our derivative would be 0. So let's take a look at a second rule to help us with derivatives. Again, this expression, this d by dx that we're seeing out in front here, that's just symbolic for taking the derivative. So we're saying the derivative of something that looks like x to the n, where n can be any positive integer like 1, 2, 3, etc. The derivative is going to be nx to the n minus 1. So let's look at a few examples of this. We'll jump down to this table that we're seeing towards the bottom of the screen here. And I think let's actually start with maybe not the top row here. Let's start with something like x cubed. So the way this table is set up, we've got various functions in the left column, and what we've got in the right column are the derivatives of those functions. So let's say, for example, our function is x cubed. Well, according to the rule, let's look at the rule which we got up here. What are we supposed to do? We're supposed to bring the exponent down in front, and then we're supposed to decrease the power on the x, decrease it by 1. So if our function were x cubed, you'd bring the 3 down in front, and then you'd decrease the power on the x just by 1. So x cubed, when we take the derivative, we get 3x squared. So some other examples of that, if your function were x squared, you would have 2 times x to the 1, or in other words, 2x. If your function were x to the 90, you'd have 90x to the 89. And then let's look at this situation here. If our function were x, that's like x to the 1. If we followed the rule, we would get 1x to the 0. Derivative of x is 1. And for this case here, we want to get really quick with our derivatives. So we want to basically be able to say very quickly, if our function is x, our derivative is 1. So it's good to work through all the details once and then just sort of remember how the rule is going to work. So x to the 90, derivative is 90, x to the 89. If our function is x, derivative is 1. Okay, so that's 2 rules down. Next rule. So here's our rule, and let's look inside these square brackets here. So C is going to represent any real number. C just stands for constant. So we've got some constant times. Now this U here is going to represent a function of x. So think of that as being something like, typically it could be something like a power of x. So the setup here is we've got a number times a power of x, for example. Okay, and this d by dx that we're seeing out in front, that's just the expression for the derivative. So we're saying to take the derivative of something like c times u, what are we doing? Well, we're bringing the constant out in front, and then we're taking the derivative of the u in the usual way. So du by dx just represents derivative of u with respect to x. Okay, so this will probably become more clear in an example. Let's try this one. Let's say we want to take the derivative of 2x to the 7. Okay, well, 2 is a constant. It's just going to go out in front here. So we put the 2 out in front, and then we multiply that by the derivative of x to the 7. We know how to do that based on our previous example. So we'd get 2 times 7x to the 6, and then multiplying the 2 and the 7 together, we have 14x to the 6. Okay, now the shortcut way that we actually think about doing this in practice is if someone asks you to take the derivative of 2x to the 7, we imagine that power coming down in front and just multiplying with whatever our constant is. So we multiply the 7 and the 2 together, that gives us 14, and then we decrease the power on the x to get x to the 6. So this arrow here represents that the fact that we want to be able to do that shortcut just in one step. It's going to be so useful when we're taking derivatives. So let's break into a new page and we'll do maybe 2 or 3 just instances of this example to make sure we're clear on that. So let's try a few examples, just practicing that last rule that we saw. Let's call these A, B, C, just so we can follow along with them. So part A, let's take the derivative of negative 4x to the 7. Okay, 7 comes down, multiplies with the negative 4 to give us negative 28, and the power on the x decreases. So negative 28x to the 6. For part B, the 9 multiplies with the 3 to give 27, and then the power on the x decreases. So 27x to the 8. And then finally, for something like a let's say a constant times x, remember that the derivative of x is going to be 1. So if we did this formally, we would say, well, it's going to be our constant 6 times whatever the derivative of the x is, which is 1. But that's sort of a long-winded way to do it. Faster way to do it is just to say, oh, that's going to be 6. So it's a good shortcut to know, basically, that anytime you're taking the derivative of some constant times x, what you're going to get is just that constant. Okay, so we've now practiced this rule that we've got up at the top of the screen. Let's see another rule here. This one's pretty friendly, I would say. So this says if you're trying to take the derivative of a couple of things summed together, so if you're trying to take the derivative of the sum, all you need to do is just take the derivative of the first term and then take the derivative of the second term and add those results together. So for example, if you want to take the derivative of, say, x to the 100 plus x to the 47, we're just going to take the derivative term by term. We'd get 100 x to the 99, and then we go plus derivative of the second term, which would be 47 x to the 46. Okay, so let's do a quick just flashback over the different rules that we've seen. So first page, we saw that the derivative of a constant is 0, and we saw how to take derivatives of powers of x. Okay, then in our second page of notes, we saw what to do if you have a constant multiplied by some function of x. So basically that lets us take derivatives of things like 2x to the 7 now. And then finally we saw that you can take a derivative of a sum just by taking derivatives term by term. Okay, so that actually gives us all the building blocks that we need to now take derivatives of some polynomials. So let's do 4 quick parts here. The question is just asking us to differentiate. So that means just take the derivative, and in each case they're going to give us a function. We'll take the derivative. So part A, function is x to the 4th plus 17 root 3. So we're going to call our derivative f prime of x, just because we're getting used to that notation. So f prime of x is equal to, well, derivative of x to the 4th is 4x cubed, and then this 17 root 3 here is a constant, so its derivative is 0. So it's really like saying 4x cubed plus 0, but then we don't write down the plus 0. Okay, part B, our function is x to the 8 minus 2x. So f prime of x is going to be 8x to the 7 minus 2. So remember, anytime you're taking the derivative of something that looks like a constant times x, the derivative is just going to be whatever your constant is. Part C, let's say our function is 12x to the 6th minus 9x plus 11. So f prime of x is going to be 72x to the 5th derivative of minus 9x is negative 9, and then derivative of a constant is 0. So we just get two terms there in the derivative. Okay, and then last one, let's say our function is 3x to the fourth minus 7x cubed plus 6x squared plus 7. Here's our derivative coming up. We'll call that f prime of x. So it's going to look like 12x cubed minus 21x squared plus 12x. And then remember, derivative of a constant is 0. So when we take the derivative of the 7, we get 0. Great, so now we can take derivatives of polynomials. That's so much progress that we've made just over the course of looking at those 4 rules. So let's do a few sort of applied examples based on what we've just learned. So in this example, we're going to find the slope of the tangent line to a specific curve at a specific point. Okay, well, remember that when we're trying to find the slope of the tangent line, it's the derivative that's going to give us that slope. If our function is called y, then probably the most natural name to give to the slope of the tangent line would be y prime. But remember that you could also call it, m tan, you could call it f prime of x. So those are all different notations for the same thing. Let's call it y prime. So we're just taking the derivative. Here's our function here. Let's take the derivative and we get 6x squared minus 5. So that tells us the slope of the tangent line at any specific point, and we're specifically interested in what's happening at x equal 1. So we're going to say, okay, let's take this y prime and let's evaluate it at the point x equal negative 1. So plugging in negative 1 there, we get 6 minus 5, or in other words, 1. So that tells us the slope of the tangent line at that point. Okay, now let's go into a little bit more detail with this kind of problem. I'm going to do a second example. The question is, where does the function x cubed minus 3x have a horizontal tangent line? Okay, well, for this one, we're going to break into a new page. So where does this function have a horizontal tangent line? Let's forget about tangent lines for a second, and let's just think about horizontal lines. Let's think back to some of our previous math courses where we talked about horizontal lines. Let's think, what do we know about the slope of a horizontal line? So if our line is horizontal, slope should be 0. Now, if we're saying we want a horizontal tangent line, then we're not just saying we want the slope of to be 0. We're specifically saying we want the slope of the tangent line to be 0. Okay, so to solve the problem, we are going to need to let the slope of the tangent line equal 0. And in order to do that, we're going to need to actually calculate the slope of the tangent line first. So the way we would actually start the calculation is we'd say, well, let's calculate f prime of x. So let's look back at our function here. Our function is x cubed minus 3x. So using our derivative rules, f prime of x would be 3x squared minus 3. And the idea is that this represents the slope of the tangent line. So if we're trying to figure out where the tangent line is horizontal, then we need to figure out where the slope of the tangent line is 0. So we need to say let f prime of x equal 0. Okay, and that represents horizontal tangent line based on our sort of side discussion that we did up here. Okay, so we're going to say we want 3x squared minus 3 to equal 0, and we'll be able to solve for x doing a little bit of factoring. So let's factor a 3 out of this. 3 times x squared minus 1 equals 0. That x squared minus 1 is a difference of squares, so that factors like this, and we get a couple of different x values. So x could either equal 1 or x could equal negative 1. So now that we've got the two x values where we think the tangent line is horizontal, or where we believe that's true, let's make a quick graph of our function. just to visualize this, just a nice way to confirm that what we've done is correct. So let's look back at the original function here is x cubed minus 3x. And let's see if we can make a quick sketch. So we'll do a table of values here. X equals 0 would be a good point to use. And we believe that our tangent line is horizontal at x equal 1 and -1. So might as well put those x values in as well. Okay, so let's plug into our original function here. We'll get some y values. So y will be 0, y will be -2, and then y will be +2 when x equals -1. Okay, so let's see if we can sketch this. We'll just label our scale there. We'll label our axes to make a nice sketch. And we'll plot these points. So we got 0, 0. We've got 1, -2 here, and we've got -1, 2 here. Okay. Now, if we just think sort of roughly about what's happening here, if you put a really negative x value in here, like -1,000,000, let's say, then your function would be down here near -infinity. So the function's doing like something like this, coming up to this point, coming down through there, then it's decreasing. And then if you think about what happens if you put, say, a big positive number like 10,000 into this function here, you get a big positive y value. So that tells us that we're going to be going up like that. Talk more about curve sketching a little bit later on in the course. But what I really want to highlight here is just these 2 points here and here where the tangent line is horizontal. So there's one. There's one point, and there's another point. So when you see a question like this, it says, where does the function have a horizontal tangent line? Sometimes you'll see the question given in terms of just x values. Other times you'll see the answer given in terms of the actual points. So if we wanted to record this in terms of ordered pairs, we'd say, well, one point has x value 1, another point has x value -1, and to get the y values, what did we do? We had to plug them in to our original function because we're trying to get points that lie on that graph. So the y values that we figured out were -2 and +2. And then you can see those 2 points in our picture. So we're going to do a couple more examples here of finding the derivative. And in applications throughout physics and engineering, you're not always using the variable x. So one of the things we're going to get used to in this example is just working with different variable names. So let's look at part A here. We're given a function, it's called f, and f is equal to pi times r plus 7r to the 10. Okay, so the variable here is called r. And when we write down the derivative, there are a couple of good ways of writing down the derivative. You could say f prime. That's usually the most user-friendly way to do it, is just to use that apostrophe or that prime symbol to represent the derivative. But if you wanted to use the d notation, it's always d function divided by d variable. So if our variable is called r, it's df by dr is how we would write the derivative. So either df by dr or f prime, and let's calculate that derivative. Okay, so this is the derivative of a constant times our variable. The derivative is just going to be the constant, pi. And then derivative of 7r to the 10 will be 70r to the 9. So we just add those together. Okay, part B, we're going to warp our brains one more time. This time our function is called v. So maybe it's measuring a volume. And the variable here is called m. So v is equal to 12m cubed minus 8m squared, and we're going to find the derivative. So in terms of notation, you could call your derivative v prime, or you could call it dv by dm. Again, the pattern is d function divided by d variable. So that just means we're talking about the rate of change of the variable, or of the function v, rate of change of the function v with respect to the variable m. That's what we're doing. So our derivative is going to look like 36m squared minus 16m. So that's a little bit of practice using different variables other than x. Okay, we're going to do one more example, one final example for this video, and we'll just jump into a new page. All right, so we want to find a derivative with respect to t. So this is where the notation becomes important here. When you see this d by dt, so the dt in the denominator tells us that t is our variable. So t is what's going to be acting like the x usually does when we're taking derivatives. And then just to further emphasize this, we're saying take this derivative when r is constant. So just imagine that r is a number, t is our variable, and we want to take the derivative of this expression here with respect to t. Okay, so let's try it. Derivative of t to the 6th would be 6t to the 5. Derivative of t to the 5th, 5t to the 4th. Okay, and then when we get to this term here, this is where we have to be a little careful. So this root r is just a constant. So think of this as being a number times t to the 4th. So how would we deal with that? Well, we would take our constant, which is root r, we'd put it out in front, and then we'd multiply by the derivative of t to the 4th, which is 4t cubed. So constant out in front, and then take the derivative of the t to the 4th, which is 4t cubed. All right, we'll clean that up in the next step. Then moving over here, we've got a number times t. So remember we said before, you know, if you're taking the derivative of something like 6x with respect to x, the derivative is just going to be 6. So you're just going to be picking up the coefficient. And same thing is happening here. If we've got a number times t, the derivative with respect to t is just going to be that number. So the derivative will just be r, whatever r is. And then derivative of r to the 5th, well, r to the 5th is just a constant, just some number, so the derivative will be 0. So final answer, 6t to the 5th plus 5t to the 4th plus, we normally write our coefficients in front. You write the number first and then any constant coefficients, and then your variable at the back. So 4 root r t cubed would be the natural way to write that, and then plus r. So that was a bunch of practice with our derivative rules. Thanks for watching.